Hello, everyone. Today, I'm going to give a long presentation about my latest paper, Diffusion Forcing, Next Token Prediction Meets Full-Sequence Diffusion. It's 2024, and we've been talking about AGI. And by AGI, we're actually talking about two types of sequence models. One of them is ChatGPT-style large language models, and the other of them is Sora-like video diffusion models. However, this type of models have divergent paradigms. For large language models, we train them with next token prediction, and for video diffusion models, we train them with full sequence diffusion. It suddenly seems that both of the AGI candidates disagree with each other. Let's take a closer look. For large language models, what we actually do is called next token prediction. How does this work? Imagine that you are trying to generate a sequence. So what you do is that you prompt it with the beginning of the sequence. For example, here is once upon, and the model will generate the next token, A. And then we append this generated token A to your original prompt. Now you feed the model again with this extended sequence. It sees once upon it, and then it's asked to predict time. And then if you repeat this sampling process iteratively, it will predict the next token one by one, and eventually you get a clean, nice sequence. On the other hand, video models use full sequence diffusion. And just like image diffusions, you start with Gaussian noise, and you gradually denoise it until you get clean image. And here it is the same. So you start with a sequence of noisy images. You bring the whole sequence noise level down to get some slightly noisy video. And you iteratively apply this process and until you get a clean, nice video. Both of these types of models have their unique advantages. I will explain the details later in the presentation after we establish an important unified view. But for now, let's just take a look at an overview. For autoregressive next token models, it is really nice for tree search. For example, like in language models, you can do tree of thought. It has flexible horizon, which enables it to do tree of thought. And you have better compositionality, and you can actually also do causal uncertainty. For example, like if you want to do tree search, you do tree search because like if you go down the tree, you have more possible states and you want to have more uncertainty, right? On the other hand, there is full sequence diffusion models. Diffusion models is known for their unique ability to do guidance. And this is actually a really interesting property we will dive into later. However, for now, just remember that diffusion models can do guidance, but it doesn't have the flexibility like autoregressive models. And diffusion forcing aims to combine the best of both. It is a model that establishes a unified view of both models, achieve excellent results on many domains, such as planning, video generation, and robot imitation learning. So before we dive into the technical details, let's take a look at the unified view with diffusion. So I want everyone to remember establish this mental picture. So if we establish a coordinate system with the x-axis as time and the y-axis as noise. So what happens is that you can take a video and gradually add varying amount of noise there. And the interesting thing is that, think about this. So people have been doing masking all the time. In MAE, like in language models, people mask out tokens and try to train your model, predict the mask out token like from the context. Okay. And now think about we use noise as a kind of masking. If you do forward diffusion like to the maximum extent, what you will end up with is just white Gaussian noise. It contains zero information about the original image, right? So it's completely masking it out. And if you add zero amount of noise, there's not masking it out at all. So you get a clean image. Of course, you can do something in the middle. Like you just add a small amount of noise, and then what you will end up with is a partial masking. You mask it out partially. It's neither fully masked out. It has some information, but it's not also very clean. Okay, so if we think about this, then we can establish a unified view about previous methods. So let's take a look at next token prediction models first. These models are usually trained with teacher forcing. And the core idea of teacher forcing is that given previous like context, for example, like once upon time, like it's like once upon, and I'm asked to predict A, okay? And in the context of video, it's like you give it some clean previous frames, and you are asking it to diffuse the next token. And how do we train that? We know that to diffuse an image, what you do is like you feed the model with a noisy image and ask it to denoise it. Here it is all the same, but like in a conditional way. You feed it with clean previous frames. That is 3 tokens here. And then you feed it with a noisy image represented by this noise sign. And you ask it to denoise this noisy next image like to a clean one. And at sampling time, you do something like LLM style next token sampling, but with diffusion. So once upon a time, I'm diffusing the next word A, and I feed this like generate A to here once upon it, and I diffuse the next token time. Although in our paper, we are actually not dealing with large language models. We're actually dealing with like diffusion models. Here it's just better for understanding, like to say large language model here. So on the other hand, there are more than video models are always trained with full sequence diffusion. What does that mean? So I showed this picture earlier that you start with white Gaussian noise. And in fact, at training time, like it needs to be trained to denoise. So I will talk about training first. So what you do is that you sample some clean video from your data set. You add a little bit amount of noise to it. Particularly specifically, it's the same amount of white Gaussian noise for every single token, for every single frame. And you feed the model with this noisy video, and you ask it to denoise it to learn to generate a clean video from this noisy video. So highlight is that you add same amount level of noise to all tokens. And at sampling time, you just start with white noise. So here, like the color here, the darker blue, like represents like just higher noise level. And what happens is that you start with pure white Gaussian noise, and then you prompt your model to denoise it to a lower noise level, denoise it until you get a clean video. And here is diffusion forcing. Diffusion forcing is different by proposing that we don't need to maintain that all the time steps, all the tokens across a video have to have the same noise level. You can insert a little bit of noise to an intermediate token, but for the far future, you are allowed to like add a lot of noise or like something different. Like basically, we are saying that just take your existing video models. Previously, you add same amount of noise to every single token. Here, you just add independent varying level of noise. And we will talk about like why this is better very soon. And at sampling time, what we can do is that we suddenly get a lot of flexibility because at a training time, it has seen all kinds of combination about what is going to be at sampling time. For example, one sampling scheme could be that I just prompt my model to do autoregress sampling, next token prediction. How does that work? It is keeping all previous tokens clean. And the next token, like what you can do is like you start with pure Gaussian noise and gradually diffuse it. You can also prompt it to just like do this full sequence diffusion. Like everything starts with like white Gaussian noise and you bring level down. Because I have seen all this kind of combination as training time is flexible, right? In fact, you can do something very chaotic. For example, like here I show a picture of like you probably like diffuse the first and third token faster than the second and the fourth. You have a lot of flexibility depending on the use you want. So too long don't read. Diffusion forcing is a technique of training sequence diffusion with independent noise level per token, and you can sample in flexible ways for different applications. Okay, now with this method explained, we can talk about the actual abilities in more details. Previously, we mentioned flexible horizon. How can we achieve this with diffusion forcing? So because it's trained to denoise in arbitrary ways, sampling is incredibly flexible. So for example, you can have flexible diffusion horizon. If you just want to diffuse next token, you can just prompt it to denoise next token only. If you want to denoise next few tokens jointly, then you can just say, let's say you want to diffuse the next 2 tokens jointly, right? Like you just prompt the next 2 tokens to be full noise, less noise until it's clean. And you can even prompt it to be a full sequence model. You just denoise all future tokens jointly. That's all the like 100 tokens that bring the noise level down, just like Sora. Finally, you also have flexible sequence horizon. It's not only diffusion horizon, right? Because previously, if you make the model causal, then you can do autoregressive rollout with either of the like the first 2 schemes. you can do autoregressive next token prediction like with the scheme, like roll out as long as you want, or like you can predict the like next two tokens together and 2, 4, 6, 8, something like that. And next, you have better compositionality. So because our model have a flexible horizon, what you can do is that you can control its context length. Um, for example, let's say I have a data set that contains trajectory of diagonal walking. Usually, if you just train a model, it will just diffuse a trajectory that looks like this. It's crossing diagonally as expected. Because this is with memory, like the sequence have full context length, have full memory. However, there are certain times where we know the environment, for example, is Markovian, and my next state only depend on my current state. Then we want some way like to control the model to generate compositional like sequences that leverage this prior. So what we can do is that we can control the context length. We can cap the context length as at previous token, immediate previous token, and as a result, you can generate something like this. And you can get something without memory, and it's able to generate a sequence that turns around in the middle. And then tree search, another nice ability about autoregressive next token models. So what you can do is that given flexible context length and flexible prediction horizon, it is very efficient for you to use it for tree search, for example, like in tree of thought. And next, there is nice causal uncertainty. So for example, in decision making, we actually care about this a lot because the far future is far more uncertain than the near future. If you're making a decision, like you don't really need to care about like getting the far future like very certainly at the very beginning. You just want to take an action that is have nice expected reward overall. And what you want to do is that your future, you want to reflect that. Usually in a next token autoregressive models, the way you reflect that is you expand this tree, like you have more and more leaf nodes to brand future possible states that is growing. However, diffusion full-sequence diffusion models, of course, like could not do this. And finally, this is a unique property of diffusion. And I think it's actually a really, really beautiful property. So given a trained diffusion model Px, so that's modeled in this distribution property distribution X, okay? At test time, let's say we only want to sample it conditionally for some class Y. So that is Px conditional Y. This unique ability of diffusion allows it to sample from the conditional distribution by applying a classifier py conditional x. Of course, like in reality, it's more complicated. It's py conditional noisy x, but let's say we have this. And what we can do is, as soon as you can take a gradient with respect to input from this classifier, it could be something even more abstract, like open a clip, like if you want to do open vocabulary stuff. You can use this gradient term to add to your like diffusion score, and then you will be sampling from your conditional distribution. So each of the AGI candidates can get a subset of these abilities. However, what we actually want is some model that combines the best of both, and that is diffusion forcing. It has nice properties about flat tree search, compositionality, causal uncertainty, flexible horizon, and in addition, it could do guidance. So from this point on, we are actually talking about causal diffusion forcing because the first paper is about causal models, and you will see why this is favorable later in some like industry applications. And here we are actually talking about RNN backbone, but transformer also works. We also released the transformer code on our GitHub, and we will talk about non-causal diffusion forcing if we have time at the end. So let's start with its application in video prediction. So given two initial frames, you want to predict like a whole video. And you can see that if we apply teacher forcing and next token predictive models to this video prediction task, it will blow up very quickly. Why is this? It is because there is this famous phenomenon called compounding error. So what is teacher forcing trained on? Teacher forcing is trained to do prediction based on ground truth context, right? However, at test time, what happens is that what you feed with this model is not just ground truth context, but it also includes newly generated frames. And these newly generated frames can be perfect. They can carry errors. And as a result, because your model is never trained to be robust to this kind of little errors, it will make erroneous predictions. And if you feed that back, it will just accumulate very quickly and eventually it blows up. So what about full sequence diffusion? What you will see is that if you just train Sora style full sequence diffusion models, you can see there's something weird like whenever your video is really, really long. And here I compare like the ground truth here and diffusion forcing. And we found that full sequence diffusion models just have like really strong like inconsistency issues. For example, if you take a look at frame by frame highlight, if you take a look at frame 10, the ground truth looks like this. Diffusion forcing looks like this. Full sequence diffusion looks actually okay. Like it also kind of see the tree, right? But if you this is an action control model, you can ask it to walk forward and turn around. And it's supposed to see the same tree. Look at this tree, like it should be here. And the diffusion forcing like can actually reflect this tree relatively accurately, like on ground truth, while full sequence isn't that consistent. So why is this the case? So there is this technique called conditioning by replacement proposed by Jonathan Ho in his video diffusion paper. So what happens is that for full sequence diffusion models, what people typically do is that I just train this entire model like with noise even for context frames. In particular, like the context frame always have same noise level as generated frames. So what the model sees at training time is that you have same noise level everywhere. However, at sampling time, what you're actually feeding the model is all the distribution. Like although there is some like scaling and stuff, but like basically what happens is that you are actually feeding the model with clean context frames, and the frames that's being diffused is always this noisy version. So there's actually like a slight distribution shift between training time and sampling time using Jonathan Ho's technique. So what we also the technique that Johnson Ho also proposes is that actually not Johnson Ho, but prior work does is that when you gradually denoise your video, you start with a noisy video, right? And you denoise it. However, like after you denoise it, your context frame also get denoised a little bit. It may change. And what we do like to make the conditioning stronger is that people always during the diffusion process, like whenever the first context changes, like I just paste the ground truth context here again, and then I diffuse and I do this replacement again. I denoise it again. If it's changed, like replace it again. Okay. However, Johnson Ho actually found that conditioning by replacement is mathematically problematic, and the solution would require expensive back propagation. It's called reconstruction guidance. So this is a really like unnatural way to do things like by prior works. In contrast, diffusion forcing explicitly is trained to handle different noise level for different tokens. For example, at test time, you can prompt it such that it knows that a certain part is clean ground truth context, and the part that's being predicted is slightly noisy. So we can get conditioning out of the box by telling the model explicitly that certain part of the context can be fully trusted. This is just ground truth. Don't change it. Only change the other part. And you can get rid of all this like mathematical problems, get rid of this expensive reconstruction guidance, and do the conditioning just very naturally. There is another highlight. If you take a look at the conditioning for consistency, like as I said, if you if you use a causal model, so this is talking about causal model. If you have a causal context frame like this, look at this tree, right? It's very obvious that if we use predictive frame, then the tree should remain here. And that is a case for diffusion forcing because like you can prompt it to fully trust the first token. However, like if you use full sequence video diffusion, that is doing this replacement trick, even with this reconstruction guidance, what you will get is that the next frame already start to look problematic. Like it's already not very consistent because of the distribution issues, the distribution shift issue I've talked about. Okay, and then there is another ability of diffusion forcing that uniquely allow it to roll out much longer. So if you take a autoregressive sampling of video models, there's compounding error. So as I said earlier, model is trained to fully trust context as ground truth. But in autoregressive sampling part of the model, like part of the context is actually not just ground truth, it's generated frames, and they're imperfect, and the error just compounds. Okay, so the solution is that diffusion forcing can tell the model that generated frames are close to GT, but they are still slightly noisy. That is, previously, like the model doesn't know, like it will just treat generated frames as ground truth and it will fully trust that and compound the error. Now I tell the model that it is informative, but don't fully trust it. It's generated. It could be like slightly noisy, and just treat it as like slightly noisy. Um, of course, people may say like, but actually like the corruption mode like from generated frames are different from wedge Gaussian noise. However, we empirically find this works just very effective. And in fact, in modern diffusion models, everybody is latent diffusion. And like in latent space, things are more semantic than capture more high-level information. And so Gaussian noise in latent space actually make more sense and are very close to the actual mode of corruption, like as sampling time. So this is a technique we call stabilization. And this is a technique uniquely enabled by diffusion forcing because it's able to tell the model like what noise level to treat the context frames on. Okay, and in fact, in our diffusion forcing paper, even without sliding window, if you use RN, like you can just roll a really long. If you train like a model, you can roll it out much longer than it's trained on. Like even without sliding window, you need sliding window, and because RN like it's more like a state-based model and have more invariance, you can actually roll out really long without sliding window. And if you do a transformer-like model. If you have temporal attention, this is 3D unit plus temporal attention, you will be able to get a video that's nice and consistent. Um, and one initial question to ask here is that what if we scale up diffusion forcing beyond like RN style models? In fact, there are already a lot of industry research that already does this. For example, the latest model for Adobe that's getting integrated to Firefly is from my colleague Tian Wei. It's called From Slow Directional to Fast Causal Video Generation. It's a really nice paper. Like what they do is that they train their video model using diffusion forcing, independent noise levels for every single frame. And then they're able to train a causal video model that generates videos as you watch it. It's generating on the go, while bidirectional model is just really slow. In fact, previously there is also a viral Minecraft emulator with neural networks. That's Descartes AI's Oasis model. And basically what they train is that they train diffusion forcing on Minecraft data, and they let the users interact with it. So I think this is not the perfect model, but I think it's really interesting because you can actually interact with it in the browser, like with your keyboard. Like it's very playable. You can press E, like open inventory, and it's able to let you like drag items around. And I find this very surprising because previously when I tried Minecraft emulators using neural networks, it just doesn't have that much flexibility and won't let you interact in such a diverse way that's realistic to the game. So there are many models that trains with diffusion forcing nowadays, and I hope more are coming after this presentation. Here is also a teaser. So we ourselves already scaled up diffusion forcing to some extent. Now with more compute. And however, in diffusion forcing 2, we'll show you some stronger techniques that allows it to generate much more consistent and longer context videos. So here is a teaser. On RE10K dataset, you are able to generate this nice video of like walking into a room. This is actually a relatively small dataset that is really challenging. Previously, people are mostly doing frame interpolation, that is given 2 frames, which might be really close, like you just generate like intermediate frames. So this is a much easier task. So the video you are seeing here, like is generating from a single image, from a single view, and roll out very, very long. In fact, we roll out much longer than the maximum length the data set provides. And you can see the room looks very consistent. Another teaser about diffusion forcing 2 is also able to handle much more tokens. And it's not perfect yet, but I think it's already a big step. I think this is one thing that people criticize the Oasis model a lot, but we are able to address that very soon. So we've just finished talking about videos generation. I think another beautiful thing about diffusion forcing is its application in decision making. And here I'm going to talk about this specific application called diffusion planning. So there are prior works that also does this. The paper from Diffuser, my colleague, basically what we are saying is that given an offline RO data set of just random walks in a maze, what you are supposed to do is that at test time, you start with a starting point, you have a goal, plan a trajectory that leads to the goal. And you can actually use diffusion to do this, even if like at training time, all you see is random walk, like no goal, no starting point. So for this task, we can make it much better with diffusion forcing. And why is this the case? I think one interesting perspective is the need of causality in decision making. So let your token X be this combo, be this bundle. So that is the action, reward, and observation it is leading to. So if you are diffusing your next token XT, you are actually predicting the current action you want to take, as well as the reward and observation this action will lead to. So this is causally correct, right? Previous models, all they are doing is predicting AT, RT, and OT. So the weird thing about that is that you already observe your current observation OT, and you're asking it to diffuse another OT, and that may disagree with the current OT. And here we are diffusing the next observation, so it's actually naturally causally correct. So at test time, we sample condition previous tokens, that is previous trajectory, and you predict your next XT, and that is action to take. Now we take your predicted action AT hat, and we can receive an actual reward and actual next observation from the environment, that is RT, OT plus one. Then we can concatenate this posterior observation with the previous generated action. Notice this is what being diffused earlier. Now we see from truth, we have this posterior, like we concat it. And then we concat this xt with xt to t minus 1 as a context for the next xt prediction. So it actually behaves really like a Bayesian filtering. You have prior, you have posterior. Posterior like can update your state estimation, like given updated observation, and it's fully causally correct. And then you can use guidance. So previously, I already talked about conditional sampling, right? Previously, I said Y could be a class, for example, cat or dog for image generation. Here, your Y can be a success classifier. Y equals successful means that you are generating a high reward trajectory that actually leads to the goal. And then if you have a success classifier, you can add this gradient using guidance and guide your generation to be a planner. So previously, data set is suboptimal trajectories that just do random work. This is really bad. And if you just apply it without guidance, it will just also clone the behavior, do random work. But now let's say with a specific goal and I have a classifier towards succeeding in reaching that goal, I can append this gradient and our generation will only generate high reward trajectories that actually leads to the goal. And as a result, you can use that as a planner. In fact, in planning, it is also very important to be flexible horizon. After you already take some steps, you want to generate a shorter plan because probably like you already like exhausted like your time limit in your game, right? And it's very natural for us to be a flexible horizon model because we can act like autoregressive models and we are causal. And then there is causal uncertainty. The far future should be more uncertain than the near future. So one way to apply diffusion forcing here is that you can denoise the far future faster. Denoise the far future slower than the near future. Near future is already bring down to a really low noise level. It's relatively clean, and your far future can remain still very noisy to account for like higher uncertainty. Noticeably, this is not unique to diffusion forcing. There is one prior paper, rolling diffusion, that's actually a concurrent work that already explored this to some extent. However, I would say like this is what I call like causal uncertainty or pyramid sampling. It is just one sampling of a scheme of diffusion forcing. You don't always need to use it. Diffusion forcing is a general framework that is compatible with everything. And we found that using this causal uncertainty scheme, we can get much better planning. In fact, we haven't really explored this, but you can do tree search. You can do tree search with diffusion forcing because it's flexible horizon and it can behave like autoregressive model. So the way we do this is that consider we are doing decision making. We are trying to diffuse the next action that leads to nice expected rewards from the long horizon. And what you can do is that instead of guiding it with one specific feature, right? If you guide it with normal diffusion, you will sample a noisy trajectory and you guide it with this one possible outcome. However, because our model is causal and it can do tree search, what we can do is that to guide the immediate next action, you can roll out many, many, many features like tree search. And by rolling out many features, you can take the expected gradient and use the expected gradient to guide your next action. That is, you are guiding it with expected future, not one possible future. So you can reduce the variance and do more effective tree search with diffusion forcing. Finally, you can get better compositionality. If you're doing a maze planning, like maybe you don't want to condition on all your trajectory before, it doesn't matter. Your plan should only depend on your current location. You can leverage the compositionality. Noticeably, in diffusion forcing one, you still need to manually control this context lens. But I think that's an interesting direction to explore in the future. And in diffusion forcing two, we are already making some progress that trying to get rid of like this manual like trimming of horizon. So if we take a look at diffusion forcing's planned trajectory, so in fact, the planned diffusion process, prior models like diffuser, it will just diffuse the start and end, like the near future and far future at the same noise level, at the same uncertainty level. And diffusion forcing, it will keep more uncertainty to the future to get a better plan to the goal. In fact, it also there's the visualization here also contains techniques like tree guidance, like you sample a lot of features to guide your immediate next action. Then there is also this interesting application in long horizon imitation learning. So in imitation learning, people have seen a lot of like robot doing household tasks nowadays. And many of those are powered by imitation learning. The way we do this is typically you train a mapping from current observation to a current action. And that is a Markovian model and doesn't require any memory. And that doing tasks with memory has been proven to be really challenging. Because naively, the way you want to do this, it probably is like have a transformer or LSTM model, like summarize all previous observations and predict the next actions. However, this techniques actually overfit heavily for obvious reasons, because if you have longer context, you actually need much more data to cover the manifold. And because you have really long context at test time, it's very easy for your model to see all the distribution observations throughout this context window. As a result, like it's really challenging to do long context imitation learning. So here I am presenting one specific task that illustrates this challenge. And this task is highly non-Markovian in the sense that we are trying to achieve the goal. So, okay, let's first take a look at what is this task. Consider the task of swapping this apple and orange using a third slot. And you can only move one fruit at a time. So one valid way of doing this is that you move the apple to the third slot, move the orange to the slot that the apple was originally at, and then you finally move the apple like to the slot that the orange was originally at. Okay. And the interesting thing is that we always randomize the positions of the fruits at the very beginning. So the model sees this initial configuration, and the model also sees this initial configuration from time to time. Half of the chance. Okay. Then for a final state, so consider you are in a state like this. The apple is here, orange is here. What's your next step? There are actually two possible action sequences. One is that you can move the apple here and then move the orange here. One is that you can move the orange here, then like you don't move the apple at all. You can see that these two policies will lead to different outcomes. And the outcome should actually depend on the initial configuration of the apple orange. You need to swap them, right? However, you don't really know by observing this state alone. You don't know. You really need to recall the initial configuration. As a result, you need memory. You need memory to know like the final state of the apple and orange. And this is a task that we found to fail all the Markovian imitation learning policies. And diffusion forcing as a sequence model, it can do this just fine. But I think one key of doing this is that you don't want to overfit. And I think noise serves a kind of augmentation in it. In diffusion forcing 2 and future works, we're exploring more perspectives on this. But if you just concatenate actions and observations, as in the planning model before, you can run this on this robot imitation learning too. And you can ask your robot like to build an imitation learning policy that actually has memory. So There is also this common question I had from previous presentations. So people are wondering what is the compute overhead from diffusion forcing? Because previously, what everyone has been doing is that we train full sequence diffusion models, and the noise combination is very simple. It's uniform noise everywhere. And diffusion forcing assumes that you are training for a lot of subtasks by noising all tokens independently. However, what we empirically found is that independent noise level actually didn't add a significant compute burden. Why is this? It is because actually the majority of the complexity of the task of video generation lies in generating the image itself. Well, in reality, like people do image co-training all the time, or they just take an image generated model and try to tune this image generated model into a video diffusion model. So because the majority of the complexity is in image generation itself. Actually, the task of like relating different levels of noise and like do temporal it's like in painting is actually not comparable to the overall complexity. And we found that if we pre-train model with image diffusion, diffusion forcing is actually able to like achieve much better result than just normal diffusion, like even with just marginally more steps. So the added amount of the needed amount of extra training steps from independent noises insignificant in the overall process. In fact, there is also a strong reason that why people want to favor diffusion forcing over next token prediction, next token diffusion in particular. So if you think about next token diffusion, what you want to do is that you feed it with a lot of images that's clean, and then you feed it with a noisy image and you apply a loss. This will waste a lot of tokens. Why is this? Because for so many tokens of the whole sequence, your model is only learning to get one denoising like training loss for like one token, the next token you are predicting. This is really ineffective because maybe your training sequence have like 1,000 tokens and you only diffuse the next token. It's like you spend the compute equivalent to 1,000 tokens just to receive like one denoising training point. While diffusion forcing, if you train it with 1,000 token length like sequence, you can effectively leverage all your compute because you are training denoising tasks for all these 1,000 tokens. So actually, what we empirically found is that if you care about autoregressive diffusion model, diffusion forcing is just a must-have way to train it effectively because so you can have like a more you can saturate your compute more, actually not saturating compute more, but like you are actually applying your compute for the downstream task you actually care about. So here is another really interesting study about why is diffusion forcing good. So here is a primitive hypothesis and some of my experiments on it. So think about diffusion model Px and a conditional diffusion model Px conditional y. So turns out what people always do is that we always train Px conditional y with ground truth observation y from the real data set. And however, when y is out of distribution at sampling time, so for example, previously we already saw the case where like y is a generated token instead of ground truth token. So the behavior of an oracle model of Px conditional y is an oracle diffusion model that's said to be really good to do conditional generation. It will still fail. Why is this? Because the oracle model says that given in distribution conditioning y, I can generate in distribution x. I can generate a really nice x. However, whenever y is not in distribution, even for Oracle conditional model, it says nothing about, provides no guarantee about X being good. As a result, even if you have an Oracle diffusion model, Px conditional Y, it can still have compounding error. So the key insight from diffusion forcing is that you can noise your conditioning variable Y as well. As a result, like you can use it to like by adding noise using stabilization trick, you can make it more robust to other distribution context. So previously we talked about this example of diagonal walking. Can we do better than like manually control the context? I think like one interesting thing we really hope to explore in the future is that take a look at this. Like you have this data set. Blue is in distribution and red is out of distribution. So it's the same data set as before, like diagonal walking. So now given the first part, you're asked to predict the second part. And now I show you all distribution first part. In fact, let's skip this. And that's the end of the presentation. There are a lot of exciting future works that one can do. And in fact, we are already in the process of diffusion forcing 2 with a much stronger technique that's uniquely enabled by diffusion forcing and will generate very consistent video with longer context. Thank you for listening to my talk and welcome to visit our website for our full paper.